on the right, just like we did for a concave mirror. Here is a convex mirror. Suppose an object is kept at a finite distance away from it. Look carefully at its image formed. Can you already tell me the properties of the image by just looking at it? First of all, we conclude that the image is smaller in size compared to the object. This is very clear. The image is diminished. The light rays seem to come from the point behind the mirror, but obviously we know that no image is formed there. So this is a virtual image. Also, it's an upright image. Remember that every virtual image is an upright image. What if I move the object towards the mirror? If I move the object towards the mirror, the size of the image keeps on increasing, but the size of the image with respect to the object is always smaller. What will happen if I move the object away from the mirror? As I move the object away from the mirror, the relative size of the image keeps on reducing. Also, at any finite distance away from the mirror, image formed is always a virtual image. You know what's coming next, don't you? Yes. What if the object is infinitely far away? Well, in the case of a concave mirror, when the object was infinitely far away, the image was formed at a single point. It was real, point-sized, and highly diminished image. Point size means that the whole image of the object is formed at a single point. Here too, the same thing happens. Image formed is indeed point-sized, but here the image is a virtual image. So when the object is kept at infinity, the image formed is virtual, point-sized, and highly diminished. Notice that even though the object is kept at infinity, the image is not at infinity. It is at a finite distance behind the mirror, even though the object is infinitely far away. In fact, this is the maximum distance at which image can be formed. Image in a convex mirror cannot be formed behind this point. We will now represent the image formed by a convex mirror using ray diagrams. Let's try to draw a ray diagram for this case first. This is when the object is at infinity. Our object will be the usual arrow, and suppose it's at infinity. Now if you remember, I told you that the rays of light coming from the object at infinity are considered to be parallel to each other. And we know that two rays are sufficient to draw a ray diagram, so we will take any two parallel rays striking the mirror. These rays will be reflected in such a way that laws of reflection are obeyed. We notice that the rays are diverging after reflection, and when we extend these rays backwards, they meet at a single point, which is the principal focus in this case. What does this imply? When we are looking at the image of an infinitely far away object, it appears to be formed at this single point behind the mirror. If the parallel rays are traveling in this direction, the image is still formed at a single point, which is different than the principal focus. We call this point focus, as it does not lie on the principal axis. What now? Now let's keep the object at a finite distance from the mirror and try to represent the image formed for this case using a ray diagram. So how did we proceed? We only need to take any 2 points on the object which is represented by this arrow. Find out the image of these two objects points first by drawing at least 2 rays emerging from each point. After reflection, all these rays will follow the laws of reflection. When we extend these rays backwards, we get our image locations. I repeat again that this is not a real location in space. It's only a location where the image appears to be formed. I want to pause here for a moment to tell you the reason exactly why I chose these 2 rays only. One parallel to the principal axis and the other directed towards the focal point.